Hello and welcome to Sean White's Solar and Energy Storage Podcast. Today, our very special guest is Eugene Bay, and Eugene is the CEO of Quino Energy. Quino Energy does water-based flow batteries. Welcome to the show, Eugene.
Thanks very much, Sean. Thanks for having me on.
Yeah, great. And I noticed too, by looking at your profile, is that you must be extra super smart because you have degrees and PhDs and things like that, and not just degrees and PhDs from community colleges, but Harvard and Stanford. And I guess you're near Stanford right now?
I live right next to Stanford. Yeah, I'm in Menlo Park, but I won't say that I'm extra smart. I would say I'm extra lucky.
Yeah, okay.
I have all the people in my life.
I'm sure that when you took your SAT test to get into college, to get into Harvard, you were just like, it was just all luck.
Well, to be honest, it was such a long time ago, I don't remember anymore. It probably was,
Yep. And so now you're over near Stanford, and I like going down to Palo Alto to get salt and straw ice cream. You've probably been there before.
Oh, yes. I've seen it at university. I'm pretty sure I passed in front of it just a day or so ago.
Okay, well, I have to go down there and get some. So let's talk a little bit about your technology, and maybe just first we can start off by letting you tell us what is a flow battery.
Yeah, thanks very much for the opportunity. So, the way I like to think about flow batteries is kind of like a gasoline car. In a gasoline car, you've got two main components. You've got an engine, and then you've got a fuel tank, and then I suppose an air intake as well. And, with most kinds of machines, you have a fuel and you have an oxidizer, and they both react, and then you get energy out of it, right? They react inside an engine.
When you say an oxidizer with a car, that's air.
That's air, yeah. Like I've got gasoline, I've got air, I burn it, I get in and out in an engine. So a flow battery is something like that. I've got the equivalent of an engine, which you can call a power block. This power block is actually what converts chemical energy into electrical energy.
Say that again, a power
block.
Oh, power block. Okay.
Yeah, so just conceptually, it looks a lot like a fuel cell with some big differences. It doesn't need platinum or any like big catalysts, but it looks a lot like a fuel cell in terms of like how it's constructed. A lot of layers of membranes and electrodes and things like that.
Yeah, I think I remember in the 2020 National Electrical Code, they even told you for a flow battery to go to the article and then NEC for fuel cells.
Yeah, from the outside, they actually look very similar. And on the inside, they also are very similar. But they're not as expensive as fuel cells because you typically don't use any catalysts like platinum or something for the reaction to happen. So in a flow battery, you've got the power block, which is akin to the engine of a car.
So is that what they always call it, a power block?
That's what some people have been calling it. Really, the power block is just a unit that provides power, right, to a battery and to the user, just like how the car's engine provides power to move.
So for like a flow battery, it takes the fluids, the electrolytes that are flowing, and then I think there's like a membrane in there, and that's
right.
the power block where the exchange of electrons, I guess, goes on?
That's right. This is exactly it. So the power block allows you to extract electrons from one side and put it to the other side, and then the electrons go through your circuit and get you your electricity. Or you can put in electricity to the power block and then have the reverse reaction happening. So just backing up a little bit, the power block gets two inputs, right? It gets the fuel and it gets the oxidizer. And you can think about those as like, two liquids of a flow battery. So all batteries are really a chemical reaction, right? And this is no different. So here I've got a reservoir, I've got a tank of like fuel, which is a reducing agent. And then I've got a tank of an oxidizer, the oxidizing.
So with a flow battery, though, isn't there like two different electrolytes, like two tanks?
You're absolutely right. Yeah, there are two tanks, one of fuel, one of oxidizer, basically. That's how we can think about it.
Okay, so it's like it's not the oxygen in the air that's the oxidizer?
Sometimes. So, if you think about some like form energy, for example, and I suppose we'll be talking about that later, one of their reactants is in fact oxygen in the air.
Okay. So does a flow battery work without air then?
Yeah, so how like there's liquid oxidizers like bleach?
Sure. Okay.
Something like that, right? So
Okay.
the oxidizers that are used in most flow batteries are liquid.
Okay. So what are the different chemicals then that you have?
So the fuel, so to speak, or the negative electrolyte, sometimes we call it the anolyte or the negalite. And that material is actually, for us, we use a quinone, which is made actually from like coal tar or petroleum aromatics.
Huh.
So quinones are widely used in dyes, like colorings.
Is that any way related to quinine that they use for malaria? And
No,
okay.
even though the first four letters are the same, it's completely unrelated.
Mm-hmm.
But it's very simple. It's like three interconnected benzene rings, and then there's some appendages on the core.
Mm-hmm.
Think about it that way. And this is a redox active molecule. So it's actually very frequently used in dyes. In fact, the quinone that we use as a raw material for battery material is this orange-brown dye. I guess you can't really see a photo in this podcast, but I do have a piece of clothing made with that exact same dye.
Okay, and it's like an orange
It's an
color.
orange-brown kind of color.
Okay. Would it be like in a tie dye or something?
No, no, no. I mean, it's just a normal plain t-shirt.
Okay, great.
So we use on one side quinone, and that just comes from earth abundant, inexpensive starting materials. And on the other side, we use a compound called ferrocyanide. Despite the name, ferrocyanide isn't toxic. It's essentially cyanide ions bound to iron, and cyanide is only toxic if it's free and
Okay.
free to bind to iron in your blood. So if there's already iron there, it's fully benign.
Can you prove it to me and drink a glass right now? I'm just kidding.
If you go on YouTube, there's videos of people actually drinking this stuff. So I don't need to do it. I can just show you like somebody doing the same thing.
Okay.
I've seen it. Yep.
Uh-huh.
So after this call, I can send you a link to a video where you can see someone
Yeah.
drinking.
Maybe I'll have some for breakfast.
You have almost certainly eaten some of it without realizing. So your table salt?
Sure.
Let's say I've got a giant container of table salt, right? It's a typical anti-caking agent in table salt.
Oh, okay.
So you probably had some for breakfast already without realizing it.
All right. Yeah, I probably did. And I think I'm still alive, so that's good.
That's right, yeah.
Uh-huh.
So it's not toxic. You've
hmm
probably, eaten a couple of pounds of it in your entire lifetime.
Oh, wow. Okay. So,
But you could drink it. I don't know how it tastes like, but
mhm.
there are YouTube videos of people doing that.
Yeah, it's crazy how some things they're like healthy for you in one form and they'll kill you in another form, like chlorine gas or even water molecules. You split them up into hydrogen
So
and oxygen,
like hydrogen monoxide.
and it could be like a big
Yeah.
explosion or something, like, and otherwise it puts out fire when it's water and it starts fire when it's hydrogen.
So, cyanide's toxic because it can bind to iron in your blood, but if you already provide it stuck to iron, then it's completely fine.
Okay, don't forget to put that iron with it.
That's right.
Uh-huh.
Well, so those are our reactants. I've got a, solution of a quinone in water, and then I've got a solution of ferrocyanide in water, and both of those things are the fuel and oxidizer, respectively. And they can be charged up in a battery, in a power block, the way I described. And of course, you can pump both liquids to the power block, assuming they're charged, and then get electricity out of it.
So you have two tanks, quinone and ferrocyanide.
That's right.
And then also, I was wondering, like, do they mix it all and you have to like refresh them?
Well, yeah, you don't actually mix the liquids, but they kind of get really close to each other. And
Uh-huh.
there's membrane in between that stops them from actually mixing. Just like in a fuel cell, if you combine hydrogen and oxygen, you don't actually want them to mix because if they mix, you have an explosion, right?
Uh-huh.
Then the reaction happens like super fast and like nobody wants that.
hmm
So just like fuel cells, the power block, the engine in our case, has a membrane, and that membrane lets these two get really close together so that they, want to react, but that in a way that you force electrons to move externally to get to the other side.
Great. And so you get these like two different tanks with ferrocyanide and quinone, and then they react through this membrane that you call it, what was it, the power block?
The power block is like the engine of a car.
Okay. And so they react through that power block. And like, how long do they last before you have to replace them?
Well, just like a car, right? How long you can go without refueling just depends on the size of your gas tank.
So like how big the tanks are.
Yeah, exactly. And so that's actually a key feature of flow batteries, not just ours, but flow batteries in general, is that the bigger the tank you make, the longer you can go for without having to recharge.
So I guess you could probably say that this power block is where the power comes from, like how big the power block is
That's
how many
exactly it.
kilowatts. And then how big of a tank you have would be the kilowatt hours.
That's exactly it. Yeah. So that's actually why I like the car analogy, because
hmm
most people get it. The bigger the fuel tank, the longer you can drive before needing to stop and refuel, right? So it's something similar. And that means like, if I want something to go twice as long and just make the tank twice as big, I don't have to buy a second engine. And this is what makes flow batteries more suited for longer durations of storage rather than short duration. So if I need to go longer, then I just get a bigger tank, and more of the fuel and oxidizer.
I've always had this wonder about with flow batteries. Like with a car, could there be something like a flow battery gas station where they take out the used up electrolyte, pump it in with good electrolyte, and then they could charge that electrolyte at the gas station or the electrolyte?
It's definitely been floated more than once, but for the one really big reason, it's totally impractical. So I think there was even one company, I think it was called Faraday Future, which showed a model of a like flashy sports car and said this is going to be run on like flow battery fluids. And if you want to like refuel, you just stop at a gas station and they'll replace the liquids. So yes, that will work, but the downside of flow batteries is that they're really heavy. So like nowadays, most electric vehicles use lithium-ion batteries, right? I would say flow batteries are about 15, maybe 20 times heavier for the same amount of energy.
Well, you're really smart. Like, why don't you make them lighter?
Well, it's really hard to beat energy density of gasoline, and then
Yeah.
really hard to beat the energy density of lithium-ion. So really, what other smart people have realized before me is you don't fight that kind of battle, right? Instead, you use it for energy in places where you don't care about moving the battery around. So anyway, going back to the like flow battery car thing, yeah, if you wanted your car to have 20 miles of range, sure, go ahead, knock yourself out. But I'm guessing the average consumer doesn't want 20 miles of range on their car.
Uh-huh. Yeah. Okay. So they're quite a bit heavier.
There, but if you don't actually, care about moving it around, then like for stationary applications, like, a Tesla Powerwall
Hmm.
kind of thing, then it doesn't matter how heavy it is. What matters is how much like floor space, right? How much land area it does take up. And that is actually one thing about our flow battery and some other flow batteries that a lot of people don't realize. You may have heard about flow batteries before, and you think, okay, well, they have low energy density, and that's true, right, in terms of weight. But in terms of like energy per floor area, it can actually be several times higher than lithium-ion battery, which seems a bit hard, right?
So how is that? Because you can stack them really high?
Yeah, you can stack them really high. And the other thing is like within like a lithium ion battery. So I'm not talking about just one power wall where like literally you have one pack of
Hmm.
lithium ion batteries. I'm talking about like the big facilities where I've got hundreds of these things around.
Yeah. And you have to have like cooling systems and space between them. And
Be spaced apart by a certain distance, to stop fire from moving from one side, from spreading from one place to another. So when you look at all of it, actually, the big batteries that the grid uses in California have more or less the same energy per land area as the world's largest flow batteries. It's about 55 kilowatt hours per square meter of land area.
mhm. I imagine that you could probably just like make a tank unlimited depth, right?
Yep, that's
Hmm.
exactly it. So, if you drive around to like some ports or shipping terminals, you'll probably have seen like, dozens of these like gigantic storage tanks, which certainly store like crude oil or kind of like oil
Yeah,
products.
sure. Hmm.
Yeah, so those things, I think they're 40 feet high. I want to say 40 feet high. And some that get even taller than that. So in a flow battery, you could actually use the space or volume available to you very effectively. You don't have like dead volume, right? Or just
Uh-huh.
space which is like wasted because, you can't stack them high. You can't cram them into too closely together or it'll catch fire or
Yeah, they're like with lithium ion, they're always worried about thermal runaway. So, like something catching fire. And so, with a flow battery, I guess you don't have any
everything's
considerations.
dissolved in water. So try as you might, it won't catch fire at all.
Like you could go light it with a match or whatever. There's no way.
Yeah, well, it's just water. So
Yeah, and I always tell people too, like with the energy density and specific energy, the more energy you put in a smaller area, the more likely it is to catch fire. Like the worst would be
like
gasoline. Yeah.
gasoline's flammable, right? But
Yeah.
gasoline has that energy density.
Hmm.
So, it's important if you care about like mobility applications or transport or
Hmm.
you're running some drones, right? But if it's just going to sit there and be part of the electric grid, then it doesn't actually matter how heavy it is. What matters is how much land area it takes up.
Uh-huh. Okay. Have you heard of anybody doing flow batteries with huge tanks like you're talking about? Like you would see like with like the oil storage facilities and things like that?
I have. I mean, It's not just us, but there's some in China too who are pushing for this approach. And there's, maybe I shouldn't name names, but mostly you're seeing this kind of innovation happening in East Asia. So typically flow batteries use vanadium. Vanadium, like I think 90% of the world's supply comes from China and Russia. So you can immediately see, well, that's kind of bad news if you're in the United States, right?
Mm.
And there's a Trump administration coming in. And vanadium is usually dissolved in very strong acid. So for that, usually you need to have like glass-lined tanks or you need to have like plastic tanks. Whereas most existing giant tanks that you see are made of steel, and that's going to get corroded immediately with vanadium.
Okay.
But our material actually is fully compatible with steel because it's mildly alkaline pH. So, we can kind of use those tanks without much modification at all. Whereas vanadium, well, you could probably do it if you did some giant some liners or something to repurpose an existing tank. But some people are just building out like, brand new plastic tanks, giant plastic tanks to store their vanadium.
Okay. And so I think with vanadium too, they have I think what you called the analyte, is it the catholyte that would be the other side? Anode
That's
and
right. Yeah.
cathode.
So the catholyte is like the oxidizer and the anolyte is like the fuel.
And so with vanadium, it's on both sides, right?
Yeah. So yeah, for vanadium flow battery, it's the same thing on both sides. It's just vanadium's in one form which acts as the fuel, and vanadium's in another form which acts as an oxidizer on the other side. So that makes it pretty convenient, right? Because it's all vanadium everywhere.
Hmm.
So it's more tolerant of like mistakes or excursions of like operating parameters
Hmm.
because it's all the same thing everywhere. So at the end of the day, like let's say I totally messed up my battery, you can just like open the valve, mix everything back up again, and then start over.
Yeah, so like with vanadium, since you have it on both sides of the membrane or, the power block, I guess you wouldn't worry about like cross contamination. Do you worry about, getting a little bit of iron or the cyanide on the side that has the quinone and a little quinone on the ferrocyanide side? Or
So
how
it's
does that?
important to have a good membrane.
Uh-huh. Yeah.
And also it's important to have good plumbing so that
Mm.
it doesn't leak, right? And, our company doesn't develop the power block at all. We just work with a number of different suppliers. But unfortunately, the vanadium flow batteries, they've been around for, I think, 40 years, maybe longer, maybe 50 years. And so the industry has had plenty of time to perfect a power block that doesn't leak, have membranes that don't puncture as well. So we're just using those exact same power blocks with minimal modification, and they're already very reliable. So we measure the rate at which, like, the quinone or the ferrocyanide kind of cross over the membrane of their own accord. It's like 10% of the battery in 100 years. So you're probably good there.
Hmm. So you started doing this 100 years ago?
Ah, I
Yeah.
wish. No, we've only been around for 3.5 years.
Okay, great.
It's not like we came up with the idea 3.5 years ago. The technology's been licensed from Harvard University, and Harvard first started working on it maybe 11 years ago.
Okay. Is anybody else doing it besides your company?
Anyone else doing it? Yeah,
Mhm.
there are a few trying to use organic materials for flow batteries, but for various reasons, we think none of them are working. So the biggest problem with using organics in flow batteries, in principle, they're cheap, right? They come from earth abundant materials, but to manufacture them at even modest scale, sometimes the cost can be incredibly expensive. And so sometimes it's tempting to go one way where you build an even more complex and amazing organic material for storing electricity and which doesn't degrade. And degradation's the biggest problem of using organics. They're designed to burn up, right? Or get turned into something else like permanently. So it's possible to like get really fancy and design something which doesn't degrade, but then there's a cost associated with that. It's really, really hard to find an organic material which is both cheap to manufacture and doesn't degrade. And we have that technology.
Great. So it doesn't degrade, or 10% every 100 years. So, you could last 1,000 years maybe. We'll have to test that.
Yeah. So, if you don't cycle the battery and you just let these things circulate, the rate of crossover is 10% every 100
Yeah.
years. I suspect that the battery will have to be replaced long before that, of course. And then when you're operating this thing, when let's say you cycle it from 0% state of charge to 100% state of charge, which you can do,
Hmm.
unlike for a lithium-ion battery, right now we're seeing degradation rate of 0.17% per year. So that's actually
Wow.
more than 10 times lower than
Wow.
equivalent LFP batteries.
0.17% per year degradation. That's like pretty close to nothing. It could just be like maybe it even gets better after a year.
Well, yeah, you never know, right? It's kind of like a rounding error.
Yeah, I know. Yeah.
But this is when you're cycling it from 0% theoretical state of charge to 100%. Unlike for lithium ion, you can't actually cycle all the way to zero or all the way to 100% or
It's bad for it.
right?
Yeah, like I always keep my car that has, well, it's got the NCA batteries in it.
Okay, so you're an early adopter.
Yeah, yeah. Uh-huh. It's a 2015 Model S and with free supercharging for life. And so I always keep it between 20 and 80. It seems to work pretty well, but I rarely would charge it more than 80%. And so that is one of the big benefits of all kinds of flow batteries is you can go from 0% to 100%. And it doesn't hurt the battery at all. So there's not also that questioning like, oh, should I go more or should I not? Or, how long is it going to reduce the life of my battery? Things like that. And so that's kind of good to know that you could just go from 100 to 0. And how do you define 100%? It's just you can't charge it anymore?
Yeah, that's when all of the fuel has been charged.
Yeah, it's just as charged as you can
No
get.
more left to charge, yeah.
And then what if you charged it beyond that? Would anything happen?
Well, then you'd start making hydrogen gas.
Okay.
So you'd start doing water splitting. But it's very easy to control because in flow batteries and also in vanadium flow batteries, like once you reach a state where it's fully charged, the charging voltage jumps up very rapidly. So it's pretty easy to control that.
So I have an idea for you. Like
Yeah.
you make some kind of like hybrid system where after it gets fully charged, then all of a sudden you got more electricity, you're an electrolyzer. So you're making hydrogen.
So, that's actually interesting because this actually opens up a whole new part I could tell you about. Making hydrogen is actually really bad for flow batteries.
Oh, uh-huh.
Yeah, and a lot of people don't realize this. So this is actually a problem which actually people want to suppress the formation of hydrogen to the greatest extent possible. And this has been actually a real problem with some other kinds of flow batteries to date. And that's hydrogen evolution. So if I charge a battery and I make hydrogen gas, you could think, oh yeah, I could maybe use the hydrogen for something. I've got an electrolyzer over here, right? But what happens is that, hydrogen means I'm losing energy from one side of my battery, right? And what that means is like, essentially, my oxidizer is getting more and more charged up. I'm getting more and more oxidizer. And then the fuel, which is hydrogen, is escaping. It's just leaving, right? So if you let this go on, then you end up with too much oxidizer and too little fuel. The fuel is mostly in its spent state. And that is what we call being unbalanced. And if it's unbalanced, I gotta have a fuel and oxidizer, right? I can't have just like half of it is fuel and half of it is like spent fuel. Then my capacity has dropped by 50%.
So we don't want to do that.
So yeah, everyone wants to avoid making hydrogen.
Okay.
When it becomes unbalanced, it also causes pH changes because if you form hydrogen, you form hydroxide at the same time. It's just thermodynamics. This is how it works. And hydroxide sometimes causes flow batteries to fail. So everyone is trying their hardest to avoid making hydrogen.
So one of the things about lithium ion batteries is you need to have like cooling and heating systems to keep those battery cells at the right temperature so they last longer. I think actually like the Nissan Leaf, when their first version came out, didn't work so well because they weren't good enough at keeping those batteries cool. So with a flow battery, is there a temperature range that you need to keep it, or is it a wider range, or how's that?
So, I mean, in principle, you could go to about, 50, 60 degrees Celsius, and our flow batteries can go up to 60 degrees Celsius.
So 60 degrees Celsius is what's that, 140 Fahrenheit? I think so. Yeah, it's 140 Fahrenheit.
You're right. It is exactly 140 degrees Fahrenheit. But the thing about flow batteries is that, everything's dissolved in water, right? So there's just a giant thermal mass over there. Most people aren't concerned about hot spots, for example. Everything's water, it takes quite a while to heat this thing up. But also on the flip side, it takes a while for it to cool down, particularly if, tanks are like gigantic, right? Then it's probably going to hold the heat quite well. So,
well, probably there's not really a chance of it getting that hot, is there? I mean, that's pretty hot.
If your battery is, say, 80% efficient, that means 20% is heat, right?
Oh, okay. So if you had a smaller tank of electrolyte, then that would be more of a concern, I guess, perhaps.
It would be less of a concern. Because you can dissipate easily, right? Smaller
okay.
tank, you can dissipate more easily.
Okay, I was thinking of these big, giant, 40-foot tall container
Yeah,
tanks?
so if they're really giant, then you need to have a separate cooling system as well, like a heat.
Oh, put them through some kind of radiator or something like
Yeah,
that.
exactly.
Yeah.
The interesting thing about flow batteries is that, well, some flow batteries like ours is that you don't actually need to like provide refrigeration, like I can just have a heat sink that exchanges and temperature of the air outside
Mhm.
and just normalizes the outside temperature.
Yeah, so it sounds like it could be much wider range of temperature than for a lithium ion battery.
I'd say a wider range of operating temperatures.
Yeah, operating temperatures.
Not so easy to compare because like lithium-ion batteries can get pretty hot momentarily, but as long as you take the heat away quickly enough, it's okay. So
Hmm.
it's like, well, I would say that thermal management is a lot simpler for flow
Hmm.
batteries.
Yeah. And then how about how cold? I guess it's sort of water based.
It is
Do you,
water-based, yeah, but I've dissolved a lot of salt in water, right? So like probably I think like vanadium goes to minus 20 degrees Celsius. But also when you have giant tanks, like you actually have a problem of wanting to dissipate heat rather than like worrying that I'm getting too cold.
uh-huh. So like how cold can the ferrocyanide and quinone get?
We haven't done much low temperature testing, but I my guess is it'll be at least minus 10 degrees Celsius as well.
Mm-hmm. Yeah, before it just like would freeze or something and then
That's 14 Fahrenheit. But yeah, when you operate the battery, it makes heat. So
yeah. So it's not much of a problem unless somebody wanted to have like the flow battery in their cabin in the center of Alaska or something.
yeah, and you don't cycle it for like 2 months.
Hmm.
That will be a problem. But really,
Hmm.
we think that most people who buy flow batteries or our flow battery will want to use it every single day. Because,
Hmm.
I mean, let's face it, if you're big enough to be thinking about having a standalone battery in your house or your facility, every time you cycle the battery, you save money or you make money. You want to, just in terms of, making back your investment, you probably want to be cycling this every single day.
Okay. So one of the big benefits that they talk about for flow batteries and hydrogen would be what they call LDS for long duration energy storage. What is your definition of LDES? I know there could be like different
Yeah, that's
definitions.
right. People haven't really come to much agreement on what exactly is LDES, right? On the short end and the long end. I mean, for us, we're targeting, 8 to 40 hours of storage, and then more specifically, 8 to 12 hours of storage.
Hmm. Okay.
And LDES, I've heard people say anything more than 4 hours to 1,000 hours is LDES. Other people have a narrower range, but essentially, I think most people agree it's like anything more than like, 6 or 8 hours is
Okay.
LDES.
Yeah, because then sometimes you even hear people talking about seasonal storage.
That's right. But that's a totally different market that you don't really want to be involved with.
Okay. Yep.
Because like I said, like every time the user cycles the battery, they either make money or they save money. So someone who can use the battery more frequently in the day, in the year, will be able to pay more, right? Whereas if I have something which maybe 10 times a year, then it has to be a lot cheaper. So that's kind of like the continuum where, short duration storage can be more expensive. But as you get to longer and longer durations, it has to become a lot cheaper. And that's where people have realized that lithium ion isn't the, like silver bullet for everything, right? Like as you get to long and longer durations, remember that car engine I told you about. Now for lithium ion batteries, I have to buy a heck of a lot of engines to go for like 10 hours, for example, or 20 hours. So the cost doesn't drop with storage duration the way that it does for, say, flow batteries.
Great. Okay. And so, how about round trip efficiency? I know that like you have lithium ion is really good, somewhere around 95%. Then you have like on the other end of the spectrum, hydrogen, somewhere around 35%. And how about your technology?
Yeah, that's the thing about flow batteries, which confuses people. So remember the car analogy I said? Like
Sure.
I can have a car that like runs at 6,000 RPMs all the time and has like terrible gas mileage. Or it can have a bigger engine and run at, 2,000 RPMs and get better MPGs, right? So it's exactly the same thing with flow batteries. Actually, you can get pretty much any kind of round trip efficiency you want. It's just like, do you want to pay for it or not? So if I've got a really big power block, it's efficient. So for example, our batteries, we can bring it up to 90% efficiency. But then, I've got like this oversized power block, which I don't know, maybe it makes sense if your cost of electricity is high and you need it to be
Or
efficient.
your cost of your power block, I guess.
Yeah, or your power block's really cheap, right?
Hmm.
But most flow batteries are just sized in such a way that the round trip efficiency is around 75%. And that just strikes a balance between the cost and size of your power block and, the round trip efficiency of the battery.
So what are these like prices of the power block and then the prices of the electrolyte?
I want to be careful. I don't give away any confidential information. So let me talk about the US Department of Energy's prices, right, that they model for power block and electrolyte. So the US DOE thinks that I think 2028, don't sue me for maybe getting the year wrong, but like 5 years out, the cost of a power block is $200 or $250 a kilowatt. So our battery reactance is $40 a kilowatt hour. And so if I have a 10-hour battery, then I take the price of the power block divided by the number of hours. Dollars per kilowatt, divide that by hours, I get dollars per kilowatt hour. So you take
Okay.
that $250 per kilowatt number divided by 10 hours for a 10-hour battery, and it adds $25 per kilowatt hour to the price of battery. And then you add the price of the electrolyte, $40 a kilowatt hour, and so then you get $65 a kilowatt hour.
And that's getting you the DC kilowatt hours.
That's DC, yeah. So it doesn't include like inverters and other power electronics.
Great.
That part is kind of universal.
We interrupt you for a very important announcement. Sean White's Solar and Energy Storage Podcast has been brought to you by Sean White's Solar and Energy Storage Podcast. That's right, Sean White is sponsoring his own podcast, and he wants to remind you to go check out some of his classes. You can go to SolarSean, that's solar, SEAN.com, and then click on the links to check out his classes. You can check out his heat spring classes, and you can also hire him to teach classes for you, like at your company, something like that. Now back to the show. So that's what you're looking for. And I guess the DOE believes in your technology because I read that they gave you some money.
They did, yes. When our company was just getting started, I paid myself $100 a month for quite a while.
You have to do that for 100 years.
Hopefully not.
Then it sounds good. No, okay.
Yeah, I know. But yeah, when, I left my previous job at Xerox PARC because of this funding opportunity that was put out by DOE, I'm like, oh, well, it's now or never. So I left my job and then we applied for this funding. And long story short, we did, in fact, get the funding.
Mm-hmm. Great. And so are you still getting $100 a month?
No, but it feels like that.
What did you do with that $100? Did you buy ice cream?
You know what? I can tell you now, I'm still paying myself minimum wage.
Uh-huh.
All the rest of my team makes way more than me.
Okay. All right. Well, I'm sure it'll pay off.
I hope so. And I'm very optimistic that it will because we've been able to grow this technology really rapidly. So, our innovation is around the materials, right? The fuel and oxidizer. And so we're not in the business of building engines or cars, right? If I've got a wonder fuel for a car, I'm not going to go build my own car. I'm going to buy like a Toyota and that's exactly what we've been doing. So our company's been able to grow very rapidly because you can just take commercial flow battery hardware, put in our liquid, and it works.
Mm-hmm.
And so if you come to our lab in San Leandro, California, just really close to the airport, there you can see 4 commercial systems that are running with our electrolyte material.
Great.
And we got a microgrid hooked up to one of those. So our offices are powered by solar panels on the roof and then batteries, one of our batteries.
Great. Awesome. Okay. And so another thing, like you getting paid $100 a month. So you have a lot of science degrees and things like that. And so you're a CEO of a company. Maybe you need to get a business degree if you're only getting paid $100 a month. I'm just teasing you. How is that I know that's very common too for engineers to go into managing companies. So it's like a big change, I guess.
Not exactly, actually. Mm-hmm. So I had some experience doing this before. I guess I'd like to call myself a 1.5-time entrepreneur because I did something very similar to what I'm doing now when I was in my previous job at Xerox PARC. You heard about Xerox PARC?
You know what? I was reading your background and I did see some things about Xerox and I was going to ask you about that.
Yeah, so PARC, or the Palo Alto Research Center, that's actually in Palo Alto.
Oh, okay.
280 and Page Mill Road, that's where it is. And that's the place where, according to Silicon Valley lore, Steve Jobs came and stole lots of ideas, right?
Stole the mouse.
Yeah, for
the mouse idea.
The graphical user interface.
Uh-huh.
That's the Xerox PARC.
Oh, okay. All right. So did you go there and do what Steve did and steal some things yourself? You get some...
No, I got inspired instead.
You got inspired. And that's pretty neat. And so is Xerox still a company?
Xerox is still a company, but okay. Xerox PARC, so this is not related to batteries at all, but Xerox PARC was donated by Xerox to SRI.
Oh, okay. All right.
And SRI is mostly based in Menlo Park.
And what does SRI stand for?
think it's Stanford Research Institute.
Stanford Research Institute.
It's not part of Stanford University, though.
Okay, great. What was that you just said? Xerox.
PARC, P-A-R-C, Palo Alto Research Center.
And did you say it was owned by Stanford?
No, Xerox PARC, P-A-R-C, was owned by Xerox. And now it's part of a company called SRI.
Okay, Stanford Research Institute.
I think that's it. Well, it's just called SRI International.
Okay.
Yeah, so originally it was called the Stanford Research Institute. Then they just called themselves, we're just SRI.
Okay, great.
I don't know, maybe they were forced to drop the Stanford name or something, but
Yeah.
SRI.
And so I saw too, when I was looking at your profile, is you did something there for desalination.
That's right, redox-flow desalination.
So it's kind of similar to what you're doing now too, because you have membranes and you're diffusing things through membranes. And
So back then, I was like laying the groundwork to spin off a startup company, which will be doing desalination for various purposes. That's actually now been spun off into another company called Mojave Energy Systems. I believe they're based in Sunnyvale, though I don't have anything to do with the company. And so they're doing essentially desalination, but not for drinking water. It's for air conditioning. I could go on another completely different podcast show and tell you about air conditioning.
let's do it.
And
Yeah.
desalination has to do with air conditioning, but I guess we'll have to leave it as a teaser for another day.
Okay. Yeah, that sounds like a good idea. And so desalination, of course, that's very important too. But it does sound like it's, kind of related to what you're doing with like flow batteries and things like that.
It's actually very similar. So the desalination technology that I invented and commercialized is actually redox flow desalination. And instead of, moving electrons to like fuels and oxidizers, I'm moving ions from like, one kind of water to a different kind of water.
So, yeah, well, maybe we could do this again and we could talk about that kind of stuff. And so another thing that just kind of reminds me of it, I think maybe 10 years ago or something, I read an article about some company was researching mixing fresh water and salt water and getting energy out of it.
That's a phenomenon called reverse electrodialysis.
You would know how to do that.
It looks like a lot like a flow battery, but in one case I've got like ocean water, and on the other side I've got like river water. So you will locate this like where a river meets the ocean.
Yeah. Well, how about I'll meet you where the river meets the ocean and we'll do that.
Well, so, there have been a number of trials, especially in the Netherlands about that, but the energy density is like awful. So it's like pretty limitless, but
Well, the ocean is pretty heavy. Yeah.
yeah, so I mean, the water is always going to mix anyway, right? So you will extract energy from it, but the maintenance costs are really high because if I'm bringing in water from outside, it's going to cause biofouling. That's the biggest problem. And not only that, the energy you get out from one of those power blocks, like if it was a flow battery, let's say a flow battery will get you 10 kilowatts, the same size system will get you maybe 100 watts.
I guess it's also like desalination in reverse,
Yeah.
like salination.
If you put in energy to make fresh and salty water, then you can mix fresh and salty water and get electricity out. That's what they're doing, yeah, but the energy efficiency is not great for that one. And it's the fouling, which is the biggest concern.
Okay.
We looked into that too, by the way.
Okay, cool.
I could also spend another podcast telling you about reverse electrodialysis.
Okay, well, let's do it. Okay. And then considering our main topic, we're talking about your company. So anything else that you want to cover or talk about?
Yeah, so, I also wanted to touch on supply chains a little bit because I think that's going to be a concern, right? As we're going into a Trump administration, you see trade tensions with China going up and, every day seems like there's talk of a new tariff. And so if you're in the lithium-ion battery industry and you're not like Elon Musk, you're probably sweating quite a bit because you're thinking, well, my prices of my imported batteries are going to go up like crazy. I've got to find out some way to go and build these in the USA. And for our flow batteries, the materials are in fact made in the USA as well. And not only that, right, it comes from like abundant materials like coal tar. So, all the way upstream. I guess that there are positives that we can see for ourselves here. The other thing as well is, for manufacturing, it has to come down in price really cheaply, right? Even at modest scales. This is part of our technology that I'm really proud of. We've got a continuous flow zero waste process that just takes the dye. Basically, it's like dye and one other chemical goes in. We zap it with electricity using a modified flow battery power block, in fact. And then the material which comes out is transformed already into the flow battery reactant. And the stuff which comes out, it can be used directly. We have been using it directly, and you don't need to clean it up at all. There's no purification. It just goes in, gets transformed, comes out, and you use it immediately. that is what has allowed us to come down the cost curve rapidly.
Great.
So in 2025, you'll see that we think our costs will be on par with vanadium. And so then if you have something which doesn't use critical materials like vanadium, but has a lower cost, then everyone in vanadium, we think, will be switching over to us.
Great.
That we think is going to happen in 2025. So coming real soon.
Unless the vanadium industry comes after you, sends their...
Well, 90% of the world's production is in Russia and China, so something tells me that's not going to be anytime soon.
Okay, well, that's great. Okay, well, thanks for inventing all of this stuff.
Oh, it's not me. It's like an entire team of people working together.
Great.
Before me and after me, who've actually should be the ones taking the credit. I just happen to be at the right place at the right time.
Great, great. And I'm imagining that probably this would be for larger energy storage systems, not residential.
Yeah, that's pretty much, I think, in line with what we want to do and also what a lot of other flow battery companies want to do. Would you rather have 1,000 small customers or one PG&E as your customer?
Yeah, 2 PG&Es, 5.
That's one thing, but also like flow batteries just become easier to operate and cheaper the bigger they get. Like the giant tank thing, right?
Sure.
Will you build 1,000 small tanks or one giant tank?
Yeah.
The costs become more compelling and the maintenance also becomes easier the bigger it gets. And that's one more thing about maintenance. It's like, how often do you maintain your air conditioner before it breaks, right? With flow batteries, because you have moving parts, regular preventative maintenance is important. And so if I sold it to the average residential customer, they probably won't do anything to it until it broke. And if you have liquids, it could be a problem. So most likely, the users are anyone who has like a dedicated facilities manager, someone to oversee maintenance and operation of these things. So probably, yeah, we'll be coming to your house anytime soon.
Okay, great.
If you want to undertake it yourself, you could, but I won't be able to support something like that.
Great. Okay. Well, it's been a pleasure talking to you. How can people find you and your company?
Well, you can find us by going online, quinoenergy.com, Quino energy.com. Or you can just find my name on LinkedIn as well, where we try to post regularly our exciting updates on our technology and also our progress on projects.
Great. Okay.
Please catch us over there.
Great. And then your last name is spelled B-E-H for Bay, Eugene Bay.
Like Bay Area.
Yep. All right. Great. Awesome. Well, it's been great talking to you, and I can't wait to talk to you again.
Like Sean, if you want me to come on and talk about water treatment or desalination or even air conditioning, I could spend another couple of hours talking about that.
Well, I want to know more.
Okay, so in air conditioning, I would say 80 to 90% of your electricity isn't actually on cooling the air, it's on condensing water out. It's a humidity removal, especially if you live in Florida, for example. And you can kind of see on a hot, humid day, I've got a cold glass of water, right? I've got condensation on it. Because condensing water releases a lot of heat. Actually, most of your electricity use in air conditioners is condensing water, it's humidity removal. So it's it's not the heat, it's the humidity. And so you can actually absorb humidity into a salt solution. You know how I leave a whole bunch of calcium chloride or something around and that sort of stuff used to melt snow? And if you just leave it out, it'll absorb humidity from the air and turn it into a giant puddle of liquid. So concentrated salt solutions can absorb humidity from the air spontaneously. And so what that means is that if it absorbs water from the air, my salt gets dilute, right? And I need to make it strong. I need to make it concentrated again. So that's how you use desalination, certain kinds of desalination technologies, to reconcentrate the salt, and then you discard the water.
Wow.
And so you regenerate this desiccant. This is called liquid desiccant air conditioning. The liquid desiccant is just a strong salt solution, basically. So in this case, you use desalination to regenerate the strong salt solution, and then you discard the water. So it's a little different here. You want to keep the salt. You don't want the water.
Wow. So it's like a different way of doing air conditioning.
That's right, yeah. And this is really good because normally in an air conditioner, you must provide electricity, you must provide energy to condense the water. Here though, you condense the water, the condensation happens spontaneously. It happens without any energy input, right? But you have to use energy to regenerate the concentrated salt solution. But here's the difference. The difference is when I have a dilute salt solution and I get out my concentrate again and the water doesn't need to get re-evaporated. The water is just separated as a liquid.
Oh,
So previously, people tried this. It didn't work really well. That's because they had to heat it up to boil the salt solution and drive off the water. But that uses a lot of electricity or energy, right? Like if I have to boil water, I have to add in a lot of energy. So my technology allowed you to separate water from these salt solutions. Like we're talking really concentrated salts here, way beyond what you can do with reverse osmosis or regular electrodialysis. If you can separate the water as a liquid, then suddenly the amount of energy you need to pay to do that becomes way lower than what it normally is. Like, I make a cold surface and have to condense water out.
hmm.
So it's like a way to circumvent the thermodynamics of air conditioning. And that allows you to get, I think on aggregate, that allows you to cut your air conditioner's energy use by about 60%, which is huge. Like, everyone's air conditioner is the same, right?
Hmm.
But this is like a totally different way of cooling air that doesn't have the same thermodynamic limitations as a regular air conditioner.
So I think what you're saying too is it's like when you change the state from, you go to like liquid, gas, and solid, when you do a state change, it takes a lot of energy,
That's right.
right?
So you want the place where you are providing energy to be only on a process that doesn't involve a state change.
Wow.
So
Okay.
here, water vapor gets in contact with concentrated salt and it just gets absorbed directly,
hmm
right? And this process releases heat because water has
hmm
condensed into a liquid base. When it releases heat, normally that has to be taken away by your air conditioner. But
hmm
here, this releases heat, it warms up, and you can bleed the heat off using a heat exchanger, which doesn't use much electricity or energy, right? I'm just exchanging energy with the air outside. So then once that heat has been bled off, then you can go and regenerate the salt solution by separating the water from the salt.
I wonder if you can invent something that does three things all at once, that does air conditioning, desalination, and a flow battery. What do you think? All at
It
once.
could, the same hardware could in fact be used as a flow battery. You're absolutely right.
Wow. I think you're onto something.
I don't know if in San Francisco, most people don't have dehumidifiers, but if you do, you can see like you run it one day and you see, wow, I've collected this much water from the air. You have that same amount of output coming out from like one of those air conditioning systems, even more if you live in like Florida or something.
hmm
And that water could be used to flush toilets or something. So, it's not really certified for drinking, but you could use it to flush toilets or something.
Uh-huh. Okay. I'm sure you could probably purify it for drinking.
Yeah, probably you could, and like with RO or something, I don't know, or UV, whatever it is, but you could use it for drinking too. So imagine you have, a cabin with no water supply. Well, you could just get your water from the air, right? Actually, that also gets us into another part of the water energy nexus called water harvesting, where, I've got a remote location that's got no wells. It's like the middle of the desert. How do I get water? Well, I pull it from the air.
I've heard about that. Yeah. So you would be good on making a space station or a Mars colony.
Well, there's definitely no water on in space, I can tell you
Uh-huh.
that. But in the desert, right, for
hmm
example, or just somewhere really remote where there's no water you can drill a
Yep.
well for. So,
Sure.
you could do that. I think there are probably better and easier ways of getting water than trying to form it in the air. Usually the places that don't have water supplies are really arid, so the air itself doesn't have that much water, so it is harder.
Yeah, yeah. Uh-huh. Okay.
But yeah, there've been some. I think Google X was trying, like, X the Moonshot Factory. Have you heard of those guys?
They're like an incubator, like the X Prize and all that.
I know it's part of Google. It's like the Skunk Works. I
hmm
think maybe they had a project like that. Don't quote me on that part though.
hmm Okay.
But
Great.
some people have been looking into like water harvesting.
Great.
Maybe if you want to live in Monterey County, but then you have no water rights, so you can't build a house, maybe you can think about, hey, maybe I can have a water harvester, then I don't need a water supply.
Take it out of the air until somebody says, "Hey, that's my air."
Yeah, that's right.
Great.
So, that it's actually all really fascinating. The other part is the water energy nexus. And that's where I spent maybe 5 years of my life at Xerox Park, getting really deep into weeds on.
Wow.
Yeah, most people are thinking, what does desalination have to do with air conditioning, right? This thing called liquid desiccant air conditioning is actually really a desalination problem.
That's pretty neat. Wow.
But
Okay.
if I'm trying to do air conditioning, it makes no sense to go and boil my desiccant, right? Then I got to cool it down again
hmm
before it can be used.
So then you sort of like desalinate it.
Yeah, so then there's
Mhm.
actually air conditioning that uses natural gas to burn. You burn natural gas to do air conditioning.
Yeah, you know what? I remember like my dad had a trailer out in the woods in the 90s, and that's where I first, experiencing solar. We had a little solar system there. And he had a refrigerator that was propane. And so there's like a little pilot light in the refrigerator. It was like, what? Fire making cold?
Oh, wow. Those are really old. Yeah.
And I think that actually there's something called an Einstein refrigerator. Are you familiar with that?
No, I haven't
Like
heard of that.
Einstein and one of his students came up with some sort of refrigerator that worked, actually had like took the heat from the sun and made cooling.
Isn't it just like solar panels with extra steps?
Well, it wasn't solar electric.
Oh, I see. Yeah, just
Yeah.
like the same way you had a propane-based refrigerator, right?
Yeah.
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 Okay. Well,
Yeah.
yeah, the very first refrigerators used ammonia,
Mm-hmm. Yeah.
and I believe that's called an absorption chiller is the name.
Okay. Yeah.
Anyway, like that's a whole different industry now.
Awesome. All right. Well, thank you so much.
Thank you very much for having me on today, Sean.
All right. And thanks for listening to Sean White's Solar and Energy Storage Podcast. To find out more about solar storage, get yourself NABCEP certified, go to SEAN, that's solarshawn.com.